Okay, let's take this example. For the diodes to be on, assuming they're silicon diode, you need 0.7 volts from here to there, 0.7 from here to there, 0.7 from here to there. That will make it 2.1 volt here. And for the transistor to be on, you need plus to minus 0.7, which makes this voltage here, that's the emitter. So the voltage of the emitter will have to be, if that transistor is on, it has to be 2.1 minus the 0.7, which is 1.4 volts. That means the current through the emitter, that's the current coming down, I sub E, has to be the voltage across that, which is VE minus 0 divided by 400 ohms. So that's 1.4 over 400 ohms. And what does that equal to? 1.4 divided by 400 is 0.003. That's 3.5 milliamp. Now let's take I didn't give you a value for beta, but we'll see if we need it. I probably can do the problem without it. Now, I know the current coming down is that value. I know the voltage here is 2.1. Can we find what this current is? This is we'll call it I sub x. Well, I sub x is going to be what? 20 minus 2.1 divided by 10K. What's that? 17.9? 20 minus 2.1. 17.9 divided by 10. That's 1.79 milliamp. Let's assume, for the sake of discussion, that for this example has a beta equals, let's pick a number. Eric, what do you want to use for a number for beta?
Can it be anything?
Any number, like between usually 85 to 100.
Let's use 95.
95. So I know I sub E here. KCL said there's I sub C coming down. There's I sub B going in. We know I sub E is equal to I sub B plus I sub C. But if this is an active mode, if this transistor is in active mode, I sub C is equal to beta times I sub B. And that's going to be 1 plus beta I sub B. Now I should be able to solve for I sub B. We know what I sub B, 3.5. Beta is 95 plus 1, that's 96 times I sub B. Can I get I sub B? 3.5 divided by 96, which is 0.036 or 36 microamps. Really small current going through the base. And if you know I sub B and I sub E, you can find I sub C. I sub C plus I sub B, which is 36 microamps, should equal I sub E, which is what? 3.5 milliamp. So what is I sub C equal to? 3.5 minus that number, which is 3.464 roughly milliamp. Well, this is the collector here. That means I know what the voltage across the collector. The voltage right there, or at the collector, is going to be what? The 20 volts minus the drop right here, which is what? 5.4K times I sub C, which is 3.464 milliamp, and we are going to have a problem.
Take a bad number.
There's going to be some negative value. Yep. Which is 1 point, now I came out with positive actually, 1.294. And what's VCE? It's VC minus VE, and that would be 1.294 minus the VE, which is 1.4, and now we have a negative number, and that can't be. That's a negative 0.1056. For an NPN transistor, that's what we have, NPN, negative, positive, negative. This voltage has to be positive. Positive on the top, negative on the bottom. This voltage has to be higher than this. So that can't be.
It wouldn't mean that the NPN would just flip?
Nope.
No?
Nope.
So you can't physically do it?
Nope, the assumption here made, this is actually in active mode, maybe it's wrong. So maybe it's in saturation. When you have 20 volts here, this voltage is going to be high enough to turn it on, but the question is it in active mode, normal mode, or is it in saturation? So this tells me it's not really in active mode. Let's see if it's in saturation. So let's assume that the transistor is in saturation. If it's in saturation, this is what we know. Same circuit, 400 ohms. We said this voltage here, 2.1 volt. From the previous case, we did that here. We said this voltage here is 1.4. That's E here. If you are in saturation, that means the voltage here for silicon is 0.2. Oh, that's 20, not 30 here. So I sub E is not going to change. I sub E is still going to be 1.4 divided by the 400, which is 3.5 milliamp. Now, if this is 1.4, then this voltage here, the collector, VC, is going to be what? 0.2 higher than this. That's 1.6. So what's this current? That's I sub C. It's going to be 20 minus the 1.6 divided by 5.4K. Hopefully it's going to be less than that, because it can't be more than I sub E. And you divide that by 5.4, and that's 3.41. And if that's the case, then I know what I sub B is, because that makes sense now, which is I sub E minus I sub C. And I sub B is going to be 3.5 minus 3.41. What is that? 3.5 minus 3.41, 0.09 milliamp, or 90 microamps. So this transistor was actually in saturation mode. It was not in active mode. So my second assumption is correct. So that's how we deal with this problem. Let me try a different one. Oh, let's take a fun one. Let's put a transistor within a transistor. Let's take 16 here. 1K, and that's your resistor. And now here, we have a resistor here of 1K ohm. It's going down right here. Another transistor and 200 ohms. And let's assume this voltage here is 2 volts. The question is, can you tell me what V out is going to be? Right here, what's V out? Well, that's really VE for the second one. If I call this number 2, this is collector 2, this is collector 1, and this is emitter 1. That's what I'm looking for. So I can find the current through the emitter 1. We'll call that I emitter 1. Down here. How do we find it? Well, if this is 2 volts, that's big enough to turn this one on. There's plus to minus 0.7. Okay. 0.7. 2 minus 0.7, the voltage at E1 is going to be 2 minus 0.7, which is what? 1.3 volts. The current through this one, the emitter 1, is going to be 1.3 volts minus nothing, which is 0, divided by the 200 ohm. That's 6.5 milliamp. If we assume this current is 0 going to that, then this current roughly, that's I collector 1, is going to be approximately equal to that one. As we said, the current going to the base of these, with all these transistors, very small. Sometimes we neglect them, especially if you try and do a quick calculations. So if I neglect this, I said this current 0 and this current 0, then I know what that current, this current coming down here, is going to equal to this one, because that's a 0. So that's going to equal to 6.5 milliamp. So can I find the voltage at C1? That's going to equal the 16 minus this resistor, which is 1K times 6.5 milliamp. And that will make it what? 9.5 volt. That happens to be the same voltage at the base of this transistor, transistor number 2. So if this is 9.5 here, that means this voltage here is going to be 0.7 less than that. So what is 9.5 minus the 0.7? So 9.5 minus the 0.7 is equal to 8.8. And that's my answer for that voltage. V out is actually 8.8 volts. In many of these calculations, we make the assumption that I sub B is 0 and I sub E is equal to I sub C. So if we make these quick assumptions, now we might be off by 0.1 here. If we really include the values, I can live with a 0.1 volt difference. So that's how you solve this problem. Let's try one more, then we'll call it quit. Let's attach this to ground. I'm going to do it backward here. attach a 2.2K here, going through a transistor, and this end is attached to negative 12 volts. And let me put a diode here, silicon diode. Put a resistor here of 1K. Put a Zener diode here. And let's put a 15K up there. I'm just having fun with this. And let's assume beta for this problem equals 30. And VBE, that's the base to the emitter, is 0.7. And VCE, if it's in saturation, I'm not sure if it is or not, but if it is 0.2. And I don't know, we can ask for anything, maybe VCE to see if it's in saturation or not. Let's analyze this and go through it. Well, if this is negative 12, that's the voltage right here. Remember, for this to be on, this voltage has to be what? This voltage has to be 0.7 volts higher. So if this is negative 12, then this end has to be what? Negative 11.3. And if this is silicon diode, this end has to be 0.7 higher than that. So add 0.7 to that, this voltage will be what? Is it 10.4? Well, let's see. Negative 11.3 plus 0.7, negative 10.6. And let's assume this Zener diode to be in reverse mode. We need a voltage here of 5 volts. So this end has to be 5 volts higher than this. Well, if this is negative 12, what's 5 higher than that? Is that negative 7? This end has to be negative 7 volts to make it negative 12. Negative 7, 5 more, that'll make it negative 12. So if that's the case, I can tell you what this current now, that's I sub B. So I sub B is going to equal to what? The negative 7 volts minus this voltage here, which is 10 point, minus a minus, that's a plus, divided by 1K. That's a large voltage actually going through it. When I make these problems, I don't think about them. I should have made that resistor much larger because that's a large current going through it. That's 3.6 amp. If that's 3.6, that means I sub C is going to equal what? Beta times I sub B. Now I'm assuming this is in active mode, not in saturation. So if this is active, that's going to be 30 times 3.6 milliamp. So times 30, that's going to be 108 milliamps. So what's the voltage at C here? Is 0 minus 2.2 times 108 milliamp. Again, that's a large negative value. Which is negative 237.6 volts. Good luck getting that value when this is negative 12. Again, the same assumption. I made the assumption this is in active mode. This one tells me no, it's not. So if it's not in active mode, I can't use these ratios. I can't say I sub C equals beta times I sub B. That's only when it's in active mode. So maybe my transistor is in saturation. So let's assume saturation. I sub B is not going to change. Again, still a high number. But if it's saturation, we know this voltage is negative 12 right here. Same as this. And this end is 0.2 higher in saturation. So this is VC is equal to what? Is going to equal to 11.8 with the minus sign. So what is I sub C coming down? So I sub C is going to equal to 0 minus a minus will make it a plus. So what is 11.8 divided by 2.2? That's 5.36 milliamp. That makes sense now, because that we know I sub E is going to equal to I sub C plus I sub B, and I sub C is 5.36 milliamp, and I sub B is 3.6 milliamp. When you add them, that is 8.96 milliamp. Again, large values, but these are crazy numbers I made up there. So my assumption that this is in saturation, it is the true assumption. Otherwise, you're going to have a minus value up there, a huge value, which doesn't make any sense. And I'll stop here.